In the heart of Rotterdam, where the river Rotte once shaped the land, engineers faced a challenge unlike any other. Last week, we uncovered the hidden battle beneath one of the city's most iconic landmarks, the Markthal, built on reclaimed land with layers of soft peat, clay, and sand. The ground was anything but stable, and just 3 meters below the surface, a high water table threatened everything. As excavation began, trouble surged from below. Upward seepage brought in brackish water, rich in iron and nitrates, turning groundwater management into a high-stakes game. The deeper they dug, the greater the pressure. The risk of bottom heave, flooding, and even collapse loomed large. The excavation pits, if mishandled, could rupture. Roads could sink. Entire structures could shift. To carve out the Markthal's massive 15-meter deep foundation and underground parking, engineers had to defy the elements, crafting bold solutions to hold back the water and tame the trembling earth beneath their feet. Before the first shovel touched the ground, engineers knew they had to build a fortress, not above the surface, but around it. A complete enclosure wrapped around the construction site, engineered to resist the immense lateral forces caused by hydrostatic pressure from surrounding groundwater. To do this, a combined wall system was chosen, a powerful assembly of steel pipe piles and AZ-type steel sheet piles. The 1,020mm steel pipe piles were driven 32 meters into the ground using vibratory hammers. Between these piles, AZ 14-770 sheet piles slid into place, locked together to form an unbroken wall of steel. Around 20 meters of continuous wall structure. Across the site, 168 meters of AZ-18 sheet piles were installed for the main pit. In the archaeological excavation pit, a separate 100 meters around, AZ-36 by 21 to 24 meter sheet pile wall was installed. The combined wall systems are essential in supporting the arch structure in the construction of Markthal. This system enhances site stability by resisting lateral soil pressure, limiting groundwater infiltration, and preventing soil movement or collapse. The system consists of 2 main components, tube piles and pairs of intermediary sheet piles. Sheet piles are installed side by side with interlocking edges to form a continuous, wall-like barrier. These sheet piles transfer the soil and water pressures to the tube piles, which are designed to bear both bending and vertical loads. The tube piles carry most of the load and are 30% longer than the sheet piles. The combined wall system plays a crucial role in site stability by resisting lateral soil pressure, minimizing groundwater infiltration, and preventing soil movement and collapse. By the sheet piles into the construction, the overall stability of the excavation was enhanced, ensuring that the Markthal's foundation remained robust against groundwater pressure and lateral soil movement. Under the Markthal, 4 different types of foundation piles were used. Pile driving of vibro piles was performed at the entrance to the parking garage. Additionally, 2,270 vibro combi poles were installed. To support the concrete strut frames, 122 steel tubular piles were used. In total, no less than 2,500 piles were driven to support the foundation of the Markthal. The Markthal had a great depth of the excavation pit, which reached 15 meters below street level. The pit had to be stabilized against the upward pressure of groundwater, To counteract this force, the piles initially served as tension piles. In the final stage of construction, these same piles transitioned into compression piles, supporting the weight of the Markthal structure. Let's see how the piles handle underwater soil through skin friction. These piles act like a tensile pile. Tensile piles, also known as tension or uplift piles, resist upward forces caused by hydrostatic pressure. In our site, which is clayey, the effectiveness of these piles depends on the interaction with the surrounding soil through skin friction. When the pile is driven into an oversized hole within clay soil, concrete grouting was used to restore the pile-soil interaction. By filling the annular space between the pile and surrounding soil with concrete, the grouting ensures intimate contact, restores skin friction, and enhances the pile's tensile capacity, thereby increasing its load-bearing capability. The construction process involved driving 30-meter-long steel pipe piles into the ground. Inside these steel pipes, 15-meter-long concrete piles were placed. The tops of these piles were positioned 15 meters below ground level. The space between the steel and square concrete piles was filled with concrete and soil, enhancing friction resistance. Once this process was complete, the steel pipes were removed. After pile driving, deeper excavation was required. However, the sheet piles needed additional reinforcement. To stabilize the excavation, a concrete strut frame was constructed. This frame prevents the sheet pile walls from being pushed inward during deeper digging. The strut frame serves a dual purpose. It holds back lateral earth pressure. First, it will become the future -1 floor. Second, integrating construction and design smartly. This base floor is built extra thick for strength, but includes temporary openings. These are closed later to complete the floor slab. Groundwater is lowered, and old foundations, including wooden piles and masonry remnants, are removed. This approach aligns with the top-down construction method, where permanent structural elements are used early in the excavation process. To safely excavate down to 15 meters, the construction pit was filled with water. This water provides necessary counter-pressure to balance soil and prevent uplift or collapse of retaining walls. Floating pontoons give cranes access across the water-filled pit. Red and white floats mark the open spaces of the strut frame. As the crane arm must not touch the concrete frame, extreme precision is required. At the bottom of the pit, 246 old piles remain. These were digitally mapped, and the crane operator uses GPS for precise digging. The crane operator located the old piles using GPS-guided crane systems, carefully removed one by one. To reduce soil transport, a silt depot filters out sediment from the water. This process reduces truck traffic dramatically, from 250 trucks per day to just 12. At 15 meters depth, a thick layer of mud covers the bottom. Divers locate new pile tops and screw in threaded rods. After that, they lay down a 0.5 meter gravel layer to prevent mixing with the concrete. Meanwhile, rebar cages are welded on land and assembled underwater by divers. Underwater concrete work went on for 3 days and 3 nights. Underwater workers operate in near total darkness at 15 meters depth. They locate the pile tops, screw in threaded rods, and lay down gravel to avoid contamination. Steel rebar cages are welded on land and assembled underwater by divers. It's time-consuming but essential for the foundation slab. Once everything was prepared, underwater concrete pouring began. A 1.5-meter thick slab was poured at the bottom of the pit. This required 2 special concrete pumps and around 1,500 mixer truck deliveries. In total, 14,000 to 16,000 cubic meters of underwater concrete was poured. This specialized concrete can be placed underwater without mixing with surrounding water, as the reinforcement is already in place on the bottom and the concrete must spread evenly across it. The biggest challenge is keeping all machines running. Any stoppage would create a joint, a weak spot in the slab. Divers monitored coverage in real time, while the concrete is left to cure underwater. The construction teams take part in a dragon boat race on the water. Over the course of 2 weeks, the construction pit is gradually pumped dry, approximately 14 million liters of water at a rate of 3 centimeters per hour. This slow pace allows the pressure on the foundation to increase steadily and safely. The sheet pile walls are tightly interlocked and watertight, while the underwater concrete floor is smooth, level, and 1.5 meters thick, forming a solid foundation for the Markthal. Minor water leakages were managed by pumps, and the immense structural forces naturally compressed and sealed any cracks. The strut frame has been pushed inward by about 4 centimeters due to soil pressure, but this remains well within acceptable tolerances. Ultimately, the process reveals a watertight and structurally sound base capable of supporting loads of up to 12,000 kilograms per square meter. Today, we looked at the engineering solutions used in the Markthal project to overcome significant underwater construction challenges. After laying 480 tons of reinforcement, a 1.5-meter thick underwater concrete floor was poured and allowed to harden. Once set, the water was gradually pumped out, revealing a smooth, watertight floor capable of supporting up to 12,000 kilograms per square meter. With the foundation successfully completed, construction is now progressing according to plan. The focus has shifted from excavation and deep foundation work to building upward. For the first time, the deepest point of the Markthal has become visible, a major milestone that was celebrated with local residents, marking a proud and symbolic moment for both Rotterdam and the Netherlands. Clear evidence of months of groundwork can now be seen. Rebar cages, threaded rods, and anchors protrude from the gently curved concrete floor, awaiting the final finishing layer. This surface will ultimately support the heavy loads planned for the space above. The next significant phase is the construction of a 4-level underground parking garage, including retail and loading zones at the -1 level. This year-long process involves continuous concrete pouring, day and night, using more than 5,500 concrete mixers. To reduce the weight of the concrete slabs, plastic spheres are embedded within the floor structures, an innovative approach to optimize strength while minimizing mass. In just 5 months, the 3 underground garage levels are completed. After 3.5 years, the entire concrete substructure is finished, and work begins on the superstructure, including the Markthal's signature arch. This iconic arch is constructed from concrete with steel cables supporting massive glass facades at either end. Inside, the structure will be brought to life with a spectacular, multicolored mural, creating a vibrant and immersive interior atmosphere.